today we're doing one of just two lectures dealing with chemistry. So this is Chemistry Week, which for some of you might be kind of exciting. For some of you it might be kind of stressful because that was maybe not one of your most pleasant experiences back in the glory days of high school or whenever you may have taken chemistry. So we're going to tackle chemistry in kind of a maybe simplistic way. When I was an undergrad way back, I spent a whole year in general chemistry and a whole year of organic chemistry. And we're doing general chemistry in one lecture, and organic chemistry in one lecture. So that means I'm not cramming, a year's worth of information in one lecture. I'm going to cover things that I think that you'll need to understand to do well on your NCLEX test. I know I will cover things that we will talk about throughout the semester and next semester. But I'm not going to cover everything. So this is another great example of when you think about how to prepare for the first exam. You're going to say, I'm really going to focus on what we talk about in lecture and specifically your lecture outline. Okay? Today I'm going to show a video clip, and this will be my second video clip. This video clip will 1,000,000% be on the exam. So it's another way of thanking you for coming to class and taking good notes. So that's where we're headed today, general chemistry. So general chemistry today, organic chemistry on Thursday. And as far as lab is concerned this week, I don't know if you noticed or you paid attention, but the summer session is 13 weeks and a normal fall or spring semester is 15 weeks. So we are trying to condense the material so you get exposed to everything in a shorter period of time. So it's weird what lab is like for the summer. Today's lab is like 45 minutes long, maybe even shorter. But next week's lab will be the full time. And next week's lab, you'll kind of leave scratching your head like, whoa, what just happened? So we're going to start out kind of easy. Last week was kind of an easy lab. Today's kind of more of a technique lab about microscopes. And then next week is a real lab, and we actually do two labs that we have in the fall in one lab period. So next week will be busy. So if you think, oh man, Mike always lets us out early on lab's a joke. Today will be kind of an easy one. Next week, not so much. All right, so that's the plan for this week. Next week, we move into the world of cells. So as I said last week, I said we start at the bottom with the organization hierarchy of talking about atoms and molecules. And this week, you might scratch your head and say, well, wait a minute, why do we care about this? But then next week, we'll get into cells, and you might get a little bit more excited. And eventually, we'll move into organs and tissues, and then there we go. And we'll be into what most people think is anatomy when we start talking about systems and processes that involve the system. But today it's chemistry, and one of the things you can see on the big screen is that we're going to focus on the anatomy of elements. That sounds real exciting. But before we get there, we're going to talk a little bit about why chemistry is important for anatomy and physiology. When we think of chemistry and its role in anatomy and physiology, one of the things that pops out for me personally is the use of medications. Maybe you are taking maybe you're taking more than one meds. And that medication that you're taking might be a little bit different than the person that's sitting next to you. For example, some of you might be on birth control, and the birth control levels of estrogen and progesterone might be a little bit different than the person sitting next to you. For example, again, when some people are taking birth control, some people have no ovulation. That's the purpose, right? So you don't get pregnant. But some women have such a high intensity of the medication that they don't even have a menstrual cycle as well. So when we think of medications, they are designed specifically for that patient. And that's cool, because when we think of the evolution of something like chemotherapy, oh my gosh, chemotherapy, that kind of chemical treatment of how we handle cancer has completely evolved. So now that it's more specific, maybe fewer side effects, even though there's still lots, but it's a lot different than it was like 10 years ago. So we're going to be looking at things like movement and digestion and heart physiology and brain activity. But for this semester, we're going to say when we think of chemistry, we're going to be talking about, in most cases, elements that are involved that are called electrolytes. And I think we all have heard about those. We know that electrolytes are in Gatorade or Powerade. But electrolytes are some type of chemical element that allows for an electrical current to flow through them. So when we think of an electrolyte like sodium, that's a big one, or potassium, or chloride, what are some of the characteristics that allow them to function so that our brain can send signals, our muscles can respond quickly? That's something to think about today. When we get into digestion and heart physiology, that's next session or next semester in 152, and you'll talk about, oh my gosh, chemicals that make up acid. We all know that our stomach contains acid. We're going to talk about heart physiology, and oh my gosh, it'll be crazy when we talk about like the effects of low potassium, low calcium on heart physiology, heart rhythms. So it's something that I would say is going to be a theme throughout the entire 151 and 152. It's just not the third lecture of the fall semester and that's it. So some of the things that we talk about today, I'm going to say circle, because that'll be worthy of truly trying to get it to sink in so that you understand this. So when I say words like cation, oh, there's a blast from the past, and ion, you immediately know what they are. And you know why they're attracted to one another. Okay, so let's move into the world of chemical elements. Some of you, when you think of an element, you might think back to that boring class in high school where there was this gigantic chart on the wall, the periodic table. Oh man. Or some of you may even had to learn or memorize parts of the periodic table. So the periodic table is a classification or organization of all the elements, and it's based upon the fact that each element has unique and individual properties. But when we talk about chemistry, one of the other words that I want you to write down in your maybe margin of your outline is the word relationship. Because when we talk about chemicals and elements interacting with one another, it's all about creating, establishing a relationship. Because some elements are really unstable. They are freaking out. They need stability. They need a partner. So they will be very aggressive to seek out stability. And then some elements are slightly unstable, and some are very lucky and are extremely stable. So the reactions that take place oftentimes require you to understand their stability. Okay, so let's draw something. I'm going to make up some type of element. Taj, right? Taj?
Yeah.
Yeah, come on, Taj, give me a little feedback. You should say, yes, Mike, I'm proud of you. Remember my name. Okay, I'm going to call this element Taj. And so whatever element that we think of or draw consists of a couple different, I think, structures. First of all, it has a core, which we call the nucleus. Okay, that's good. It has these kind of outside circular rings around the core or the nucleus. Sometimes these rings are called shells. You might remember that, high school chemistry. But it's within the nucleus that we find these different balls. Some of the balls we call protons. And some of the balls we call neutrons. So one of the things that we do to classify an element is that we need to know the number of protons. Because that's the way everything is organized in the periodic table, is the number of protons. So the number of protons is also the same as this big phrase as atomic number. If I would say, what is the atomic number of an element? Of course, I would never ask you to memorize any of those. But if I said Taj has, look, 8 protons and 9 neutrons, right now you should be able to tell me the atomic number of this element that we just created. The atomic number would be 8. If I ask you what is the atomic mass, then you look at the nucleus and you calculate the total number of neutrons and protons. So the atomic mass would be 17. So far, so good. But there's one more player when we look at an element. It's probably the biggest player in terms of establishing relationships. And that's, and those are electrons. And so electrons, look, I'm going to make special, I'm going to color them in. They exist not within the nucleus, but they hover around these shells. And I want you to write this kind of pattern down: 2, 8, 8, 8, 8. And what that means is that when you look at these shells, or these electron shells, that an element is completely stable when it has their outermost shell. In this case, so far it looks like this is the outermost shell, satisfied with these numbers. So let me say that again. An element is completely stable if it has the outermost shell reaching the maximum number of electrons. So it says the first shell has a maximum of 2. So far, jackpot, looks really, really stable. So the next one can have a maximum of 8. So let's put 8. 4, 5, 6, 7, 8. Okay, so far so good. We have 2 in the first, it reached its maximum, check. 8 in its second, so far this is unbelievably stable. Well, let's say that in the old third shell of our element Taj, look at this, we have just 1. Just 1. And it needs, look, 7 more to become happy. Now, what is the chance that it's going to find 7 free electrons? Not good. But if it simply unloads it, look, says, hey, I'll donate you to something, its outermost shell goes from having 1 to having 8. And it's unbelievably stable. So what I want you to think about today when we talk about chemistry is about relationships. We're going to talk about reactions, but it's all about stability. And if you remember this rule, 2, 8, 8, forever 8, then you understand how stable or how hyperactive an element is in order to reach or achieve stability. So that's where we're headed today. Now, a couple more things about these ingredients of an element. We're going to say protons have a positive charge. Neutrons have no charge. They're neutral. And these electrons have a negative charge. So now you get it. You get an idea of how to play the game with an element. I could give you some crazy element on the test. I could ask you some questions. Is this element, what is the atomic number? What is the atomic mass? I could ask you a question like this, and this is a good one. What or how many valence electrons? What? So what I would write down in your notes is the word valence refers to the outermost shell. In the case that we drew, we would say that an element called Taj has 1 valence electron. Now, if it donates it, it will have 8 valence electrons. So the number of valence electrons indicates really how stable the element is. Okay, so that's a lot of information. For some of you, this might be the first time that you've ever heard the words protons and neutrons and electrons. So here, let me give you a practice kind of question. This is something that you could do at home. You could practice this, and then you could send me your answer via text, and I could say, yeah, it looks good, looks good. So you might come up with an element name. Maybe it's your dog's name or something. And you could just make up some things, like, oh, the nucleus has this many neutrons and this many protons, and you can make a number of this many electrons. So just kind of write down, what is the atomic mass, what is the atomic number, and how many valence electrons? Easy kind of test question to make sure that we're all on the same page. Okay, yay. All right, so that's good. An element. Now when we look at the element in terms of its atomic number, we said that the periodic table is organized so that all of the elements and their protons are organized so that we can maybe make sense of the elements that exist. Now some of the elements are really important. In fact, out of all of the elements, 24 elements have some type of biological role. This brings us to our first slide with numbers and percentages. So here's my thing. I'm never going to ask you any number or any percentage unless I tell you. So I will never ask you 6 or 98.5 or 24. Don't memorize that. But you just want to remember that there are some that have a biological significance, sometimes in great quantity. There are some that exist and are important in very small amounts. We call these trace elements. When we look at the organization, you can see that oxygen is probably the most commonly or prevalently used element. Oxygen, look at that, 65%. And then when you get down to the crazy things like, look at this, copper and chromium and cobalt, this makes up 0.7%, which you would say, well, why do we need them? But we do. And we get a lot of these things from plant material that we eat. Plants take in a lot of these inorganic elements, and we get them from eating plants. Or some of you get them from taking a daily supplement if you're not a big plant eater. Okay, so let's talk about some of those elements that are inorganic. Inorganic means they come from the ground. Inorganic means they're not made of carbon. And when we think of inorganic structures, you can see that equals about 4%. I think it says something different on your outline, so you might have to change that. But again, I'm not into percentages, so it doesn't really matter. But when we look at minerals, they're important for enzymes and the creation of things like enamel and bone, things that are really hard in our body. And you can see that some minerals are a big player in the formation of electrolytes. Electrolytes, big topic. Now, we drew the structure of the atom or the element up on the board. You can see again that the nucleus contains protons and neutrons. We talked about atomic number, and we talked about electron shells. Notice that it says that valence electrons are in the outermost shell. And these are the electrons that establish relationships. These are the ones that interact with others. In fact, it's the electrons in the outermost shell that help determine how they behave. So valence electrons are maybe the most significant electrons. Okay, it's kind of hard for me to see, so I'm going to pull down the. Now this is an example of a situation where, you know, I would never have you like memorize any of this, but let's appreciate this. Here's carbon. That's going to be the main focus. That's the start of the show for Thursday's lecture. Carbon. Here you can see that they have a nucleus of lots of balls. It says inside this nucleus they have 6 protons and 6 neutrons, which means that we have an atomic mass of 6 plus 6. Since we have 6 protons, the atomic number is 6. If I would ask you how many valence electrons, everybody tell me right now quick, how many? 4. 4. Good. How many more does it need to be stable? Everybody? 4. 4. All right. I'm feeling good about this class. So sometimes in organic chemistry, look, we draw carbon like this. That's money. Because it says that we have 4 opportunities for it to interact with something else in order for it to be stable. That's important. That's why we draw a carbon with 4 branches. It needs 4 more. When we look at nitrogen, you can go through the same pattern. You can say, oh, 5 valence electrons. That's closer to 8. And then look at sodium. Sodium is kind of like our Taj element. It has that one kind of rebellious, lonely valence electron. So instead of trying to find 7, it's going to look for a friend, look, like, well, like I'll show you in a second, like chloride, but potassium is in that same category. It has that one valence electron looking to donate. Okay, so think about this. If I gave you these numbers, you should be able to tell me a little bit about it. Okay, does everybody feel good? Okay, all right. Now, every element has a close related, let's call them cousin. Instead of saying cousin, we're going to call them isotopes. So, an isotope is an element that is exactly the same as another element, except the number of neutrons are different. And we really don't care about neutrons because they don't have any charge. But they do change the interaction or the behavior of some elements. So remember, isotopes are closely related elements with just a different number of neutrons. The only reason why I want to talk about isotopes in this class is that some of you are going to go on and do things with ultrasound or maybe with X-ray tech or something like that, or work with MRI or PET scans. And whenever you use radiation, in whatever form, heck, you could even be a dental hygienist, and anytime you use or are exposed to radiation, you're using an isotope of an element. So some elements have isotopes that when they fall apart or break, they release radiation. And we call those isotopes, right? Radioisotopes. So in my personal background, when I was an undergrad at UC, I was a biology major, and then I thought I would become a researcher and I was going to get my PhD at UC, and I got into this really good lab. I was doing molecular biology, and I was using radiation on a probably daily basis. And then it started to hit me like, you know, I'm like 23, I'm using radiation every day. I have to wear these like badges on my lab coat that kind of measure my exposure. And my lab partners sometimes would be given kind of like a red light, like you've reached your limit. you don't get to do research for a while. And then I start thinking, is it really worth it? You know, I want to have kids someday. You know, what kind of effect is this going to have on me? So for me, radiation, you know, was something that I really kind of, I don't know if fear is the right word, but I didn't want to be around it. And for some people, you're exposed to it, again, on a frequent basis, and you have to be monitored. When we think of levels of radiation, we're even being exposed to radiation in this room just by the lights in this room. Or when we go outside in the sunshine, we're exposed to UV radiation. So we're always exposed, but there's different levels, and I want to go through the different levels of radiation. So when we talk about radioactivity, it's kind of interesting that we're always being exposed to some level of radioactivity. But the good news is that most radioactivity that we are exposed to can't penetrate our skin. That's the good kind. So let's talk about the types, and we have old Marie to credit for all of our knowledge on radioactivity, and I'm not going to ask you one question about Marie. So just put your pencil down and just kind of listen. But Marie was somebody who was like obsessed with radiation. She must have been weird, right? Who wants to study radiation? But she was really kind of a pioneer. She was the first woman in France to receive a PhD. She even, look at this, won the Nobel Prize. She trained physicians how to become X-ray technicians. And unfortunately, she probably died in one of the most painful ways of radiation poisoning. Oh man. There's a lot of ways that I don't want to go. That's got to be in the top 5, radiation poisoning. But she made it to 67, and that's pretty good in 1903. That's probably equivalent to 90s now. So Marie had a long life, and what we learned from Marie is that there's different types of radiation. For example, UV light, which is in this room, X-rays, which you may be exposed to, or something as serious as nuclear decay, all have different levels of radiation activity. And we describe that radiation activity by describing them as being either alpha, that's what this is, or beta, or gamma emitters. So on the test, the first test, I'm going to ask you to explain alpha, beta, and gamma. I'm not going to ask you anything about Marie. But I want you to be able to tell me that when I say alpha, you're going to say that that's the least harmful of all the radioisotopes. Because it rarely causes problems because it cannot penetrate skin. So the good news is that this is what most researchers use in cell biology and molecular biology are alpha emitters. So that's not a problem unless you get radioactivity like in a cut or something. Then you're in a little bit of trouble because it's penetrated your skin. Beta particles are a little bit more dangerous. They have a tendency to pass through. But if you're wearing like 3 pair of gloves and you're wearing a face shield and you're using a Geiger counter, then you should be safe. So beta, even though it's more dangerous, is okay. Gamma is not okay. Gamma is the worst. Gamma is something that can kill you just by breathing it. You don't even know it's in the room. So gamma is what we associate with like natural disasters with, you know, radiation or radioactive nuclear plants. So maybe you heard of like the uranium plants that have been maybe exploding or falling apart with tsunamis or something like that. Believe it or not, in Cincinnati, we had a uranium processing plant, and it is about 5 miles from my house in Ross, and it was called Fernald. And back in the day, listen to this, you guys are all younger than me, but back in the day when my parents were growing up, my wife's parents were growing up, they were potentially exposed to some radiation. And people who lived in a certain mile radius of Ross have probably had some issues with cancer or some unexplained illness. And it was probably 5 years after I was married, so it's about 25 years ago. Fernald went out of business and everything went into massive cleanup. And then they start sending out letters to everybody within a 3-mile radius, including my wife's family. And they said, you know, have you experienced any thyroid problems, any cancer, and or listen to this, any emotional or psychological issues? And if you checked yes, yes, and yes, Fernald was going to give you some serious cash. And my wife's parents checked no, no, no. And they're regretting it. Because my wife's mom has now had 2 bouts of cancer. My wife's dad has cancer now, and it could be age-related, maybe not Fernald-related. But just being exposed to the air is something that people back then didn't really know of. Here's the worst thing about these radioisotopes, is that when we look at radioisotopes, they have 2 different lifespans. And I want you to be able to differentiate physical from biological half-life. Here we go. So physical half-life says, if we have this radioisotope in a test tube, how long will it take for half of it to decay, to disappear, in a test tube? But biological half-life says, how long will it take for half of it to disappear inside of a human body? That's different. So an alpha emitter, the safest one, the one that I used at UC when I was in grad school. There was an alpha emitter called phosphorus 32, P32. It had a biological, stay with me, right? It's a good example. It has a biological half-life of 14 days. Well, one day when I was working with P32 with a lab coat, 3 pair of gloves, and a face shield, I was safe but fearful. Somehow, I have no idea, a small drop of that radioactivity got on my brand new gym shoes. And back in the day, the gym shoes to have were shoes called K-Swiss. They were spanking new, white, like 25 stripes on them, you know? And when that drop of radioactivity fell on my gym shoes, it became an instant problem. And my research advisor, my professor said, Mike, you gotta take those shoes off. You gotta quarantine those. So that day I had to walk around, you know, in my socks, and I had to have someone bring me a pair of shoes. But my shoes were able to be recovered if you start doing the math. Now, I'm not saying shoes are a biological structure, but the physical half-life is 14 days. So in 2 weeks, there would have been half the amount of radioactivity on my shoes. Okay? 2 weeks from then, it would have been another half off. So that's another 25% off. So you can do the math and keep going down the road, but it took about 2 months for all of the radioactivity to disappear from my shoes, and I could wear them again. So 2 months, that was a hassle, you know, kind of stunk. But when you think of uranium, stay with me, uranium, it has a half-life of thousands of years. And think about that. No one in this room will even have grandkids to be able to understand what that means. So what do we do with uranium that was in Ross? We put them in a very special barrel. Who knows if it's gonna work, right? Because it's gonna be as flaming, hot, radioactive today as it will be in 1,000 years. And will the barrel still exist? Well, who knows? So we put it in a barrel, we put it in a truck, we take it out to New Mexico, we bury it in the desert in the sand. That's what people do with radioactivity. And they think that, you know, in today's technology, those barrels are going to be good for thousands of years, but who knows, you know? So when you breathe something like a gamma emitter, something that could get inside of you, there is no hope, right? It's gonna be as extremely radioactive as inside of you for, what, 100 generations? Yeah, question. Someone had a question.
I was
Jocelyn?
just gonna say, do you know where in New Mexico they
Oh,
bury it?
no.
No,
Oh,
just
I
somewhere
don't know.
out
Let's
there?
go live there. I don't know.
Oh, I did, that's why
Oh, you
I'm
did?
curious, yeah.
Oh, man, I don't know. This is probably on the set of Breaking Bad. All right, so let's move on to another interaction. We're not going to move into radioisotopes, but we're going to be talking about ions. Oh, that's a big one. Let's go back to our friend sodium, and we said sodium was like Taj. Sodium has that one valence electron. But look at our pal chlorine. Hey, look at this. It has 7 valence electrons. Oh, this is a match made in heaven. If I donate one, I instantly become stable. And if I receive one, if I'm chlorine, I become instantly stable. So sodium and chloride are like a perfect pair. And you guys get what sodium chloride is, that's table salt. So when we have a situation where elements exchange, here we go, exchange electrons, we call them, or we call the process ionization. Now, a question that I will ask you on the exam is, what is the charge of these elements? Well, before we exchange, let's do the math. We have 11 protons, 11 positive. We have 12 neutrals, so we don't care about the neutrons. And we have 11 electrons, which are negative. Look, we have 11 positive and 11 negative. So overall it's negative, it's neutral charge. Look at old chloride, 17 positives, 17 negatives. Both are neutral, but they're unstable. Look what happens when they have this process. Look, we have now how many protons? Those stay the same, but we lost an electron. So now we have more positivity than we have negativity. So now look what happens. We have a positive charge. Same thing over here. Now we have one more electron, one more negatively charged structure. So we're going to say that after ionization, we have a negative charge. Positive and negative charges. So we have names associated with that, and oh my gosh, circle and put 20 stars next to these. And anion, I will say that 20 times this semester. Before we leave on August 10th, I will say anion 20 times or more. And I want you to automatically remember tonight's lecture and say, okay, that is something that is negatively charged. Why is it negative? Because it received an extra electron. Electrons are more, look, it received an extra one, so now it has 18. That's one more than 17. It's a negatively charged. Or I'm going to talk a ton about sodium and potassium. Both of those are examples of cations. Now listen, when I say anion and cation, I'm telling you from 27 years of teaching anatomy that this is no different than teaching you 2 times 2 is 4. This is a fact that you need to know in your brain. You need to study this tonight so this becomes a fact. Anions are negative, cations are positive, and be able to explain why. Because one accepts an electron and one donates an electron. Okay, that's good. Now for some of you, you say, how does this apply to me? Why do I care about electrons and anions? Well, it's when we combine an anion and a cation together that we create salts, like sodium chloride, table salts. And there's lots of other salts. In fact, we call those salts electrolytes. Electrolytes are what allow us to conduct electrical current. So, if we are low on electrolytes, then it has huge effects. Some of you may have small children, and when your infants are having chronic diarrhea, your doctor's saying, oh my gosh, they need electrolytes. If they're puking all the time, electrolytes. Some of you will go out on a Saturday night and live it up at the bar. You'll go say, hi, man, hook me up, girlfriend. And you'll say, I am so done of puking, I need something that restores my electrolytes. You feel a little low. For me, when I'm low on electrolytes, there's a tendency for me to get a migraine headache. I get about one migraine headache a year. I got one on Saturday. I woke up on Saturday morning and I ran like 10 miles. And it was like 1,000% humidity. And I sweat like a mother. So I was running, I was feeling pretty good. And I got finished, I took off my shirt and I wrung it out. It was like gallons of sweat. It was so disgusting. I didn't really replenish my tank. And by the afternoon, I started seeing like spots, and oh my gosh, I should have known better. I had to replace my electrolytes. So without electrolytes, you can have issues with brain and muscle function. So for some of us, you can see that if we don't replace that, it can be serious. And that's why with little babies, even adults, when you have muscle cramps because of low electrolytes or brittle bones, it can cause some serious side effects. Usually when I'm running long distances, I'm drinking constantly. I usually run with those backpack things. And I'm taking electrolytes and eating things. But there was a marathon in Columbus, and I can remember almost the exact house in the neighborhood where all of my muscles locked up at the same time. It was like Charlie Horse City. I couldn't even walk. I had muscle cramps, and it was my brain saying, don't move anymore because you don't have the electrolytes to do it. So someone gave me a bunch of stuff to drink and ate, and I kind of walked it off, and then I was able to run again. But when you're low in electrolytes, it can have huge effects. So take a look. This is a diagram or a figure of some very common electrolytes. I don't want you to study any of those, but I want you to notice this, that every electrolyte in this column is a combination of a cation, look, positive, and an anion, negative. And they have a good relationship with one another. So whether it's Gatorade or Powerade, oh man, next time you drink a Powerade, look at the size of the bottle. It says ion 4. And no one knows what that means. No one. But it says that it has potassium and sodium and magnesium and calcium. These are all electrolytes that are replenished by drinking this sports drink. And if you're going to drink a sports drink, get the one with no sugar, by the way. The sports drinks are loaded with sugar. All right, let's move on to another element. Not an isotope, not an ion, but a free radical. I want you to know a little bit about free radicals. Free radicals are elements that are extremely unstable. So you can say that their valence shell is far from being satisfied. Free radicals are ones that are created by normal metabolic activity, which means you can't avoid creating them. So every day your cells make free radicals as a byproduct of just existing. You can increase your free radical numbers in your body by being exposed to radiation or doing something crazy like smoking. I hope no one here smokes. You can't be a serious nurse or medical student, in my opinion, if you really understand the horrible effects of smoking. That one of the things that happens when you smoke is that you increase free radicals. If you say, so what? Well, wait till you see this. Free radicals are like firecrackers. They attach to the membranes of cells and they blow them up. And then when they blow them up, they multiply and make more. So these are one of the most destructive things that our body deals with. If you would search, what causes aging? This is probably the number one theory. It's the accumulation of free radicals over time. So what does our body do to help prevent free radicals? it creates antioxidants. Some of you are big into that. Maybe you are a big vegetable or fruit person, or maybe you're a big supplement person, where you're trying to take things that have lots of antioxidants. Occasionally, when I'm filling up at Kroger, instead of getting that Diet Coke, which sometimes I desperately want, maybe I'll go with a sugar-free vitamin water. And one of my favorite flavors is Triple X. It means that it has triple the antioxidants. Now, I don't know if it does anything, but at least it's making you feel good. You know, it's no sugar, so that's good. So antioxidants, you can get those in many cases by eating things that are brightly colored. 3 or 4 years ago, the winner was blueberries. Now it's pomegranate and something called acai, which I don't even know what that is.
Acai.
Yeah, acai. Is that a California thing? Now, we have some situations where people say, oh, I've heard that dark chocolate, yeah, what a great excuse. Dark chocolate has a lot of antioxidants. Or, I've heard that a lot of red wine has some antioxidants. I want to talk about red wine because what they found that's in red wine is something really, really cool. They found that when the process of making wine, taking grapes and obliterating them, smashing them, they noticed that in the skins of grapes there is a element or a molecule called resveratrol. Definitely circle that. That will be on the test 1,000,000%. Resveratrol is only found in the skins of red grapes, maybe other grapes, but resveratrol is designed to protect the grapes in times of stress, like drought or whatever. So it's a way of kind of preventing damage to the grape. Or maybe you can say it's a way of preventing aging to the grape. So researchers have said, and that they've known this all along, that people who live in places of Europe or maybe Paris or wherever they eat a lot of pastries and drink a lot of wine, there's very low incidence of cardiovascular disease. It's very strange. I mean, their diet's horrible, yet there's no, problems with blood pressure. 80% of the population is not on Lipitor like it is in the United States. Why is that? So they found that resveratrol is one of the most powerful antioxidants. I got a video that I want to show you.
17 years ago, 60 Minutes first examined the so-called French paradox, which suggested that the French, despite a high-fat diet and high consumption of wine, had a remarkably low incidence of heart disease compared with Americans. Most researchers agreed that there was something in the wine that offered protection. And a few years later, even the highly cautious federal dietary guidelines say that moderate consumption of red wine can be beneficial. Now, scientists across the country have identified a substance in red wine called resveratrol that they believe might do more than just protect the heart, but could, in very high concentrations, significantly extend life by preventing a number of age-related illnesses. If they're right, we all may soon be taking a pill that could give us an extra decade or two of healthy old age.
If the promise holds true, I think this has the chance to change healthcare.
Dr. Christoph Westphal says we all may soon be taking a drug that just might beat the clock, a simple pill that could delay the inevitable.
Our goal is to prevent and forestall many of the diseases that strike us as we reach 50, 60, and 70, all with one pill.
What you're suggesting is that some kind of rejuvenation drug that turns a 70-year-old into a 35-year-old.
That might be pretty hard to do, but I think if we're on a train heading one direction, we can slow down that train. I think we can slow down these genes that control the aging process.
That quest to put death on hold began in 2003 when Westphal met David Sinclair, a biochemist at Harvard, who was studying the genetic components of aging.
5 years ago, I met David, and he had shown that you could extend lifespan in yeast. That's pretty exciting.
If you happen to be a yeast, it's very exciting.
Yeast are one thing, human beings are more complicated. So Sinclair focused on a gene present in almost all life forms, the sirtuin gene. It's normally inactive, but when it is active, Sinclair believes it triggers a survival mechanism that extends life.
Okay, that's really important. Sirtuin gene. So we all have them, but they're rarely activated. It's a gene that's only triggered when we are in desperation mode, like dying, starving. And so resveratrol is something that activates sirtuin genes. Cool.
Convinced that something in nature could activate that gene, Sinclair randomly tested thousands of compounds.
Wait a minute.
And bingo, you got a hit. Resveratrol.
When I Googled this resveratrol, I was shocked to find that red wine was the top hit.
Red wine is brimming with resveratrol. It's found in high concentrations in the skin of the grape. It seems to play a role in protecting it from invading bacteria and fungi.
Were you aware of the research into red wine that it offers health benefits?
Oh, sure. I mean, my chair when the link was made, and I thought that this was a potential explanation for the benefits of red wine.
Convinced they were on the verge of a major scientific breakthrough, Sinclair and Westphal launched Certris, a Cambridge, Massachusetts research company. They, along with a handful of other cutting-edge biotech companies, are developing resveratrol-based drugs that they believe zero in on the longevity gene.
The important news here is not that we found something in red wine. The important thing is that we passed a milestone where we can now make drugs based on this knowledge and potentially slow down aging.
Okay, so the cool thing about resveratrol is that this was a few years ago, and when I was walking, my wife gave me some list to get things at Sam's. I went in Sam's and I was walking in the supplement aisle, and I'm not a big supplement person. My wife kind of is, but I'm not. And I happened to look up and I saw that Sam's was selling a big old canister of resveratrol. My jaw dropped. And I said, I'm getting it. I am going to practice what I preach. You know? I don't take pills unless I have to. But every morning, I've been taking a resveratrol for like the last 3 or 4 years. Who knows if it's going to work? But on the side, it says that 1 pill is equivalent to like 30 glasses of red wine. I mean, you're not going to get drunk. It's just giving you the resveratrol. So my wife is taking it. You know, I've encouraged my kids to take it. I'm not encouraging you to take it, but it's something to think about, right? Definitely something to think about when you think about antioxidants.
Have you had side effects?
But there's none. There's none.
Eating grapes won't give you some.
Yeah, you'd have to eat like 1,000 pounds of grapes.
They don't have any issues with like phosphates?
Or
Because I know some people are.
Yeah, there's no phosphates in it.
Okay.
Yeah, I mean, there's literally no side effects that I'm aware of. Yeah.
And it only comes in capsules, right?
It comes in those little gelatin snap
Yeah.
things, yeah.
Like, are you able to pull the card? Because
Why
like
would I want to do that?
some people have trouble with like capsules.
Like swallowing them?
Yeah, some
You
people
can, like,
like have
sprinkle
trouble with capsules.
No, I've never had a problem with it, so I don't know. So if you have a problem with it,
I was just
start
curious.
yanking.
I know like somebody who has really big trouble with it.
No, I don't know.
You gotta be careful if it's a time release.
All right, so something is going on with my, maybe I had my clicker. I bet you I was leaning up against it. All right. Okay, so the last thing that we're going to cover today is the world of relationships and elements. And instead of saying relationships now, we're going to call them bonds, okay? So when 2 or more, molecules are attracted to one another, we call those, that reaction or that new formed product a compound. Like sodium chloride, that's a compound. Sometimes in chemistry you would write something called the chemical formula or molecular formula. And we're not going there. You don't have to write anything in chemical, nomenclature for this class. But I'm just trying to give you an overview of some of the things that you would learn. Sometimes you would draw them, like I remember doing that, not having very much fun drawing like benzene rings and things like that. None of that will be on the test. So here's some examples. You can see the structural formula, you can see the molecular formula. Sometimes you have elements or compounds that have very similar looking appearances, but maybe there's just some slight differences that can give a total different kind of reactivity or response. Don't worry about isomers. What I want you to really focus on for the last 15 minutes is these four. So I think you should be able to tell me a 2-sentence explanation about each one of these. It's just 2 sentences. If you can do that, then that'll be good enough for me. So we're going to talk about which ones are strong, which ones are weak, why are they used, and give you some examples. We're going to start with an ionic bond. So we already know what an ionic bond is. Remember, ions are in Powerade. Ions are created when we are donating or when we are receiving an electron. So it's an attraction of oppositely charged ions. So what I would write down somewhere next to your outline is that sodium chloride is the best example ever. Sodium and chloride, donating and receiving. One's positive, one's negative. It's a match made in heaven. But unfortunately, what I want you to remember is that ionic bonds are pretty weak. You take a tablespoon of salt, sodium chloride, remember that attraction? You put it into water, and all of a sudden, all the salt disappears. Because water can break ionic bonds in most cases. That's not very strong. There's water everywhere. So, ionic bonds exist, but they're not very strong. The strongest of all bonds are covalent bonds. And in this case, we're not donating electrons. We're not attracting to opposite charges. We're actually sharing. So next to the word covalent, underline the word sharing. And if we share one set of electrons, it's strong, but it's not nearly as strong as if we're sharing 2 sets or 3 sets. The more that we share, the stronger the bond. Okay, so let's talk about some covalent bonds. The strongest, whether it's single or double, obviously double would be even stronger. But now we have to use some words that I know you'll see on the end clips. So circle the words polar and nonpolar. When you think of polar, ready? I want you to think of that phrase, oh man, that person is the polar opposite of me. So when we think of polar, a lot of times it deals with elements or interactions of opposite charge. But in covalent bond terminology, we're going to say that a polar bond is one that shares electrons unequally or unfairly. It's just because of the charge and the relationship. So you're just going to say polar is unequal. Nonpolar is equal sharing. And if you'd had to rank which bond is the most stable, you would say that a non-polar covalent bond is the winner. Josh, are you okay?
Yeah.
Okay. So let's take a look. When we look at a covalent bond, one of the things you can see is that poor hydrogen. Guess what its proton, guess what its atomic number is? Ready for this? 1. How many valence electrons does it have, everybody? 1. How many does it need? 2 to be stable. So guess what it does? It hooks up with another hydrogen. And they share. and they instantly become stable. That's sweet. It's a pretty tight bond. Look at this, CO2. We know what that is. So that's the stuff that we exhale out, carbon dioxide. Look at this, it shares two sets. It's really strong. So carbon dioxide is a tough molecule to deal with.
And that's non-polar.
And that, well, yeah, no, in this case, that's a good question. So CO2 is an example of equal sharing, so this is non-polar. Yeah, good job. So here's an example of some visuals of a non-polar and a polar covalent bond. So polar means that in this case, if you're looking at OH, which is a hydroxyl, you're going to see that a lot of the electrons are favoring oxygen. It's not fair. It's unequal sharing. So that bond is tight, but it's not nearly as tight as two carbons. Look at that. Look at that. That's a tight bond because it's equal sharing. Okay. The weakest of all bonds, we're going to say for the test, are hydrogen bonds. Hydrogen bonds are something that are pretty temporary, easily broken. And one of the things about hydrogen bonds is you can see that they're attracted to something, again, related to their charge, is that they have some very important functions, even though they are the weakest of all bonds. For example, hydrogen bonds are involved with building things. And I want you to write this question down because in 3 lectures, I'm going to ask you this question, and maybe you can think of the answer in 3 lectures. That's a week and a half from now. Here's the question. Why would, write this down, why would DNA, the molecule of DNA, be held together by hydrogen bonds? Maybe some of you already know that answer, but I'm not going to tell you for 3 lectures. I mean, think how important DNA is. Why would we want the weakest bond to be in charge of holding it together? Think about that. All right, so here's some examples of some hydrogen bonds. Again, very, very weak, and that's important in terms of our relationship with water. Now, I'm going to say that the last slide of the day today, you did great, deals with a force. Sometimes people will call it a bond, but I don't want to be, it's not a trick, everybody. Here's the answer to the question on the test. If I say, what is the strongest? You're going to say non-polar covalent. If I say the weakest, everybody's going to say right off the bat, hydrogen. But if I say, what is van der Waals forces? These are brief, temporary, listen, attractions. They're not even a bond, they're so weak. So, is van der Waals weaker than hydrogen? Well, yeah, but it's not even a bond. So, I'm not trying to trick you. The answer to the test question, which is the weakest bond, would be hydrogen. The van der Waals are something that are also important in terms of temporarily building things. So we've all seen a house being built, or a business or a restaurant being built. Stay with me. And as we drive past that same house, that restaurant every day, you might see a wall being built. And as that wall is being erected, they might have like support diagonal pieces of wood to keep it up temporarily. And then those diagonal pieces are knocked down when everything starts to come together. That's what a van der Waals force is. It's very temporary to allow for something to be built. Okay, so that's extremely weak. The answer on the test is still hydrogen bonds are the weakest. Okay, now, before we move into the world of organic chemistry, I want to talk a little bit about water, and we've talked about hydrogen bonds. And when we look at water, you can see that most of our body weight is water. So we have to talk about interactions with water. A couple terms that I want you to write down. One is the word hydrophilic and hydrophobic. Hydrophilic, you can also say, is polar. Polar molecules are hydrophilic. Hydrophobic are nonpolar. When you hear the word phobic or phobia, it should make sense that molecules that are hydrophobic hate being around water. Great example would be oil or fats. When you're cooking spaghetti, you have that big pot of water, and you add some oil, it bubbles to the top. It stays on top because it doesn't want to mix with water. Hydrophilic, oh, it loves water. So if you have something that's hydrophilic, it will dissolve easily into water, like salt, right? Okay, so hydrophobic, hydrophilic. When we think about water, one of the things that's important is to remember that when we have fluids inside of us like blood, lymph, other fluids, the main ingredient is water. So the way we are able to interact with proteins and hormones, things that we find in blood, has a lot to do with how well they can dissolve in blood. Sometimes we have proteins or hormones that are hydrophobic, and they need like special carriers to transport them. Well, that'll be a big topic. Okay, so that's good. So today was a little bit more intense. Thursday, we'll continue that. So get in the groove. I'm going to tell you right away, I told my wife this. I can tell you right now that this class is going to be one of my best classes I ever had since I stayed. I can tell on the first day with the energy, and tonight I had 7 people come to office hours. That's like a world record.
I'll send you my outline.
Usually I have
so you
people
have
come
everything
after
ready.
the first test and they're like crying.
That's true.
So, yay.